Good morning and welcome to this next lecture on sound and structural vibration. Last time I said we will summarize the poles or singularities that we found. Okay, so first for m less than 1, okay, k becomes equal to kp plus epsilon kp by 4m square root of 1 minus m square. Okay, and this pole is the subsonic pole, so that is k0 here. I will stick with this cut, so that is k0 here and kp was here. Now kp gets modified to kp plus delta, that is this pole. So it is subsonic, meaning kp is greater than k0. The corresponding gamma is square root kp square minus k0 squared into 1 plus epsilon by 4m into 1 minus m square to the power 3 by 2. Okay, it's a real positive number. If you remember, the phi x comma y had this form a e to the power of minus gamma y, okay, and e to the power of I kx e to the power of minus I omega t. So we are talking gamma. So if gamma is real and positive, it's a decaying field. So this is a decaying field. Decaying sound field in y direction. So this is first. Then below m equal to 1, the second one is the one near IKP. So k, that becomes equal to IKP minus epsilon kp by 4m square root of 1 plus m squared. Okay, and the corresponding gamma okay, this pole is here IKP, but original pole, it is corrected over here. Okay, the corresponding gamma is equal to minus I square root of kp square plus k0 squared, okay, plus epsilon kp by 4m into 1 plus m squared. Okay, so this is propagating in the y direction but decaying. Okay, now I'd like to say that corresponding to this cut in the K plane, K0, K0, K plane, okay. The corresponding cut in the gamma plane was this. Okay, and for m less than 1 we have a gamma 1 here, a gamma 2 here, and a gamma 3 here. Okay, so corresponding to this gamma 3 is this root k, this being consistent. Okay, then for m greater than 1, m greater than 1, okay, first we have k is equal to k0 plus epsilon squared kp divided by twice m cube into m fourth minus 1 whole squared. Okay, greater than m greater than 1, we are in the supersonic beyond coincidence, so k0 is higher. Now this correction is further higher. Okay, so if we take k0 here, again the correction is k0 plus a delta. Okay, so this is also subsonic. So whether you are above m equal to 1 or below, there is always a subsonic pole. Okay, below m equal to 1 it's close to kp, above m equal to 1 it's close to k0. The corresponding gamma is k0 epsilon by m square into m fourth minus 1. Okay, this is a positive real quantity and therefore no sound. Okay, no sound or decaying sound in the y direction. Okay, so sound field doesn't take away energy. The energy propagates along the plate with this wave number undiminished. Okay, so that's let's call it 1 again. Okay, now second, the root near kp, okay, that's k is equal to kp plus I epsilon kp by by 4m square root of m square minus 1. Okay, this positive is chosen with reference to appropriate damping of a pole for positive x direction. Okay, then gamma, so this is let's see where it is. Okay, this is my k0 cut, it's here, okay, so this is a propagating root on the plate. This is a propagating root on the plate, but it also decays slowly. Okay, and the decay depends on the amount of damping you have. This is positive x direction. Okay. Along with that, the gamma is given by minus IKP square root of m square minus 1 into 1 minus I epsilon by 4m into m square minus 1 3 by 2. Okay, so this root, the gamma for this, how does it behave? Okay. So we have e to the power of minus gamma y. So this minus cancel, okay, and this I give a negative real value placed here. This is increasing in the y direction, okay, from the plate. Okay, then of course we have this propagating. The I imaginary part tells me it's propagating because the time is minus I omega t. So this is propagating and increasing. Okay, so it seems a little counterintuitive, right? But if you look at it another way, that my source is here, the line source is here, and this is my plate. Okay, and we seem to see that the sound field is growing. Okay, however, the x wave is decreasing. The x directional wave number is decreasing, so it will decrease as we move further and further and further. It will decrease. Okay, so here we go a little to the right and look at the sound field. It will again grow, but not so much. And you go further, it will grow, but not so much. So given that the causality or the cause lies here at the origin, okay, now if you draw a line, a radial line along any direction, you will see that the sound field is decreasing. Okay, so it's all right. Okay, so here this supersonic pole will generate some sound. Okay, and this root comes from, again, the gamma plane. How we find that this is the valid gamma plane? Okay, so there is a root here, there's a root here, and there's a gamma 1 here. So this is gamma 3, this is gamma 5, okay, there's gamma 1. So this root generates this root. Okay, lastly, the imaginary root that we have close to IKP, okay, does not change, that K is equal to IKP minus epsilon Kp by 4m square root of 1 plus m squared, okay, and the corresponding gamma is minus IKP square root of 1 plus m square into 1 plus I epsilon by 4m into 1 plus m square to the power 3 by 2. Okay, this is propagating and decaying in the y direction. Okay, so I have maintained consistency with Crichton's cut and his statements. Now we started off looking at coupled vibration field on the plate. Okay, and just to recall, the Vx was given in this form, minus I omega f by twice by b integral minus infinity to infinity gamma e to the power of I kx dk by k fourth minus kp fourth gamma minus mu kp fourth. And what did we say? This velocity field total is going to be now the I twice pi times the sum of my residues. Okay, and we found the V1x plus V2x. Okay, this was dominantly a pole at ik0 and decays as this part. Okay, and the residues were left here. Okay, so the residues have to be computed at the singularities, which we just listed, summarized. Okay, so if you look at this denominator, now there is a theorem that if we have a function that's a ratio of two polynomials, then the residue can be computed. So if you have a function, I'm not being very rigorous here, p of z by q of z, then the residue of this can be p of z over q dash of z, provided q dash of z doesn't go to 0 at whatever pole. Okay, so if we use that, we need the derivative of the denominator. So we have k fourth minus kp fourth square root of k square minus k0 square minus mu kp fourth so we need to take the derivative of this thing. Okay, so if we do that, so derivative with respect to k, so d dk of that is going to be 4k cube, sorry, 4k cube into square root of k square minus k0 square plus k fourth minus kp fourth into 1 by 2 square root of k square minus k0 square into 2k. This 2 goes, so we get 4k cube into k square minus k0 square plus k fourth minus kp fourth into k divided by square root of k square minus k0 square, and this will go on top. So if it goes on top we have gamma already. Okay, so we'll get gamma square, which is k square minus k0 square. So we have gamma already, so you have k square minus k0 square, and the denominator is going to be 4k to the power 5 and k to the power 5. So 5k to the power 5 minus 4k cube k0 squared, okay, minus kp4. So this has to be evaluated at any root, any of the roots. Okay, of course including e to the power of I kx. So if it's for this cut we have taken, if m is less than 1 you get 2 roots. If m is greater than 1 you get 3 roots. You will have the corresponding field. Okay. Now let's look at m less than 1. Consider m less than 1. So the root near kp, the correction happens to be k is equal to kp plus epsilon kp by 4m square root of 1 minus m squared. Now if m becomes small, that means I go very close to 0 frequency, m becomes order of epsilon, this m becomes order epsilon, then this epsilon and that order epsilon will cancel and this will become an order 1 term, which is not allowed in asymptotics. Okay, the correction should always be smaller, of a smaller order than the first term. Okay, so this correction is not valid anymore if we go to low frequencies. Okay, or if my square root 1 minus m square becomes order epsilon, which means 1 minus m square becomes order epsilon squared. Okay, even then this order epsilon and that order epsilon will cancel and this whole term become order 1. It's not valid. Okay, so let us now, so we have this frequency regime now. So we have this frequency regime which goes from 0 to 1, let's say. This is 1. Okay, m. So we will look at these very close to 0 and we will look at this regime close to 1. Okay. So let us now first look at very close to 1, but less than 1. Okay, so we are going to look at m close to 1, but less than 1. Okay, so how do we take a correction? So we take a correction of this form. M is equal to 1 minus epsilon square n. Okay, where do we get this idea from? We said when 1 minus m square is equal to order of epsilon squared, the expansion is invalid, and therefore I make 1 minus m square is some epsilon square into an order 1 term. This is an order 1 term, but multiplied by epsilon square it is becoming an order epsilon square term. So that's where I get this from. We can do further. Okay, so m square is equal to 1 minus epsilon square. Okay, then m is root of that, so it will become 1 minus epsilon square n by 2, still epsilon square. That's where we get this from. Okay, so we can replace n by some n square, so I mean n by n some n star. Okay, so then 1 minus epsilon square n star. So we will look at this frequency, but we will look at this particular root, which is zeta is equal to 1. Okay, so we will expand this root now using a 1 epsilon to the power beta plus a2 epsilon to the power 2 beta and so forth. Okay, because I don't know what balancing power will come in here, I do not know here. Okay, so I'm expanding in an unknown, but I will take only one term because it's simple to derive. Okay, so what do we do with this? We have to get back to our famous dispersion equation, zeta square minus m square minus epsilon by m. Okay, this has to be balanced again. So if we do that and correct till first term, I get 1 plus a 1 epsilon to the power beta 4 minus 1, okay, square root of 1 plus twice a 1 epsilon to the power beta plus a 1 square epsilon to the power 2 beta minus, okay, m is also corrected, so 1 minus twice epsilon square n plus epsilon to the power 4th n squared. Okay, minus epsilon over m. M is 1 minus epsilon square, that has to be 0. Okay, so now if we expand this, I get 1 plus 4 a 1 epsilon to the power beta till beta term minus 1. Okay, and here I get, okay, the 1 cancels away. Okay, so I get twice a 1 epsilon to the power beta, okay, plus a1 square epsilon to the power 2 beta plus twice epsilon square n, etc., minus epsilon over, and this is a small term, so it's epsilon. Okay. Now let's assume and see. Okay, let's assume that beta is at length 2. Okay, then what do I get? I get 4 a1 epsilon to the power beta, and under the square root the dominant term is twice a1 epsilon to the power beta minus epsilon should be 0. So that means I get beta plus root beta. Okay, beta plus beta by 2, sorry. So I get epsilon to the power 3 beta by 2. That has to balance this epsilon term. Okay, which means this implies 3 beta by 2 should be equal to 1, which implies beta should be equal to 2 by 10. Okay, so if we now use this So that means now I have found the correction epsilon order for the right expansion. So that means zeta should be expanded as 1 plus a1 epsilon to the power 2/3. Earlier we wrote beta and we didn't know. So now beta has been found to be 2/3. So this is the right expansion. So if we again substitute this in the dispersion equation, I get 4a1 epsilon to the power 2/3, okay, square root of twice a1 epsilon to the power 2/3, okay, and other terms, but this is the dominant term, minus epsilon equal to 0, which gives me I will just compute this, okay, a1 is equal to 1 over 2 to the power 5/3. Okay, so zeta is given by 1 plus epsilon to the power 2/3 by 2 to the power 5/3. Zeta is what? K by Kp, right? Zeta was K by Kp. So now that's the correction. That is the correction when we are very close to m equal to 1. When we are in this range of frequency, that's the correction for the zeta equal to 1 root. Okay, so it is still a perturbation. The coupled value that we found here is still a small change over the original value. Okay, so we will still call this light loading. Okay, now very low frequency. Let's try very low frequency. Let's try very low frequency. Okay, that means what? M will be taken as order epsilon. And how do we represent it? We represent it as M is equal to epsilon times another order 1 quantity 1. Okay, so at this frequency range, that means we are very close to the zero frequency, somewhere here. Okay, so let us again perturb this root 1. Okay, so we'll do 1 plus a 1 epsilon to the power beta. Okay, so we have again, we shouldn't forget the dispersion equation, 4 minus 1 square root of beta square minus m square minus epsilon over m, that is to be balanced. So I get 1 plus 4 a1 epsilon to the power beta minus 1 square root of 1 plus twice a1 epsilon to the power beta plus a1 square epsilon to the power twice beta minus m in this form, minus epsilon square m1 square minus epsilon by epsilon m1, so epsilon is equal to 0. So this is now an order 1 quantity. Okay, so if we try to find out the dominant term here, all others have epsilon to the power some value, so these are small terms. So this is order 1 term, this term is an order 1 term, okay. And here we have 4a1 into epsilon to the power beta, and therefore this is an order epsilon to the power beta term, okay. So this total term on the left is order epsilon to the power beta, and the right hand side term is order 1, okay. So no balance, there is no balance possible, no balance possible. That means what? The roots are no more perturbations to uncoupled roots. So fluid loading is not light, this is significant fluid loading. I will end the topic here. We will continue in the next class. Thanks.